In this segment, we will talk about how to differentiate between ill-conditioned and well-conditioned system of equations. So let's suppose somebody gives you a system of equations which is in the matrix form and turns out to be Ax equal to C, where A is the coefficient matrix and C is the right-hand side vector, and of course X is our solution vector or what we call as the unknown vector. So whenever we're setting up simultaneous linear equations, we write them in the form of A times X equal to C, where A is the coefficient matrix, X is the solution vector of the unknown vector, and C is the right-hand side. What you would like to see is that if you want to determine whether this particular system of equations is well-conditioned or ill-conditioned, is to say the following, that hey, if I make a small change in the elements of the A matrix, then how much change is it making in the solution vector? Or if I make a small change in my C vector, then how much change does it make in my solution vector? Because you would like that, hey, if I make a small change in the coefficient matrix, you would like the solution vector to change in a small amount. Or if you change the right-hand side vector, you would like the solution vector to also change by a small amount. Because we're going to, as we go through the process of setting up simultaneous linear equations for real life problems, those might be set up through a program where we're going to have round-off errors in the calculation of A matrix and the calculation of C matrix, let's suppose. We don't want such round-off errors or the lack of our use of precision. We may use only single precision rather than double precision or quad precision to affect adversely what the solution vector is. And if it does, we want to have a mechanism of knowing whether it is doing so. So let's look at some examples right here to see that whether you can see that from a simple example whether the system of equations is well conditioned or ill conditioned. Let's suppose somebody says, is this particular system of equations 1, 2, 3.999 xy is equal to 4, 7.999 well conditioned? Or ill conditioned? So we want to be able to make the difference between saying that, hey, if somebody gives me a system of equations like this one, is it well conditioned or ill conditioned? I can see that if I wanted to solve this set of equations, it does have a simple solution. For example, what is the solution to this one? It's 2, 1. So xy is 2, 1. So x, if you take x equal to 2 and y equal to 1, in fact, if you plug x equal to 2 and y equal to 1 in here, you will get 4 and 7.999. So that's itself the solution for that. And we want to see that whether if a small change in the coefficient matrix, is it going to result in a very different value of x and y I'm going to get? Or if I make a small change in my right-hand side vector, is it going to make a big difference in my x and y? And what I'm doing now here is, like, let's suppose I make a small change in my coefficient matrix. So what I'm doing is as follows. I'm taking 1.001. So I'm making a small change in the coefficient matrix, changing it by the thousandths. I get 3.998. So what I'm doing is that I'm making a change of about a magnitude of 0.001 for all of these elements which are right here in the coefficient matrix, and I will not change the right-hand side. And I want to see that, hey, does it make a big difference in my solution? And what I find out is that, hey, if I solve these two unknowns by hand or by using MATLAB or any kind of calculator, the answer which I get is as follows: 3.994, 0.001388. And you can see that just by watching it or just by looking at it, you can see that this value of 2 has changed to almost 4. This value of 1 has changed to almost a value of 0.001. So very different, with very small change being made in the coefficient of the A matrix. So we can very well see that, hey, this is not a well-conditioned system of equations. In order to complete the argument, let's go and change the right-hand side a little bit. So let's suppose I have 1, 2, 3.999 here. And what I do is I keep the coefficient matrix the same, but I changed the right hand side a little bit. Let me make this to be again 1/1000th of difference there, and 7.9998 here, 1/1000th of a difference right there. And let's go and see what I get for value of x and y. So I get x and y here, and if I calculate the value, I get minus 3.999 and 4.00. So again, you're finding out that from the original set of equations which we had right here, where the solution was 2 and 1, I made a very small change. I changed 4 to 4.001. I changed 7.999 to 7.998. Just a small change, small relative change in the right hand side vector. But when I solve these two equations to unknowns by using calculator, MATLAB, whatever, you find out that the solution which I get is different. This was 2, now it's minus 3.999. This was 1, and now this is becoming 4. So if somebody had to ask me just by intuition, is this a well-conditioned system of equations or ill-conditioned system of equations, I would term this to be a ill-conditioned system of equations. Now in the later segments, we'll talk about how do we do this quantitatively without having to do this. But as an illustration to illustrate the point that, hey, what does it mean that a particular system of equations is well-conditioned, ill-conditioned? This is a very good example to follow. Let's see if this system of equations is 1, 2, 2, 3, x, y well-conditioned. This system of equations, is it well-conditioned or ill-conditioned? So we just want to illustrate the fact whether it is well-conditioned or ill-conditioned. So if you look at, so I didn't put the right hand side here, there should be 4 and 7. So if we have this system of equations, is it well-conditioned or ill-conditioned? The solution to this set of equations, if you would either solve it or plug in these values of x equal to 2 and y equal to 1, you are going to get 4 and 7. Or if you solve these two equations to unknowns, you're going to get x, y equal to 2 and 1. In order to find out whether this particular system of equations is well-conditioned or ill-conditioned, I'm going to conduct two experiments. I'm going to make a small change in my coefficient matrix. So let me make a small change in my coefficient matrix. I'm going to make 1/1000th of a difference to 1. I'm going to make 2 to be 2.001. I'm going to make this to be 2.001. I'm going to make this to be 3.001. And I'm going to say xy is equal to 4 and 7. So I've not made any change to the right hand side, but I made a very small change to the coefficient matrix right here by changing the coefficients by 1/1000ths. And so what I get is xy, when I solve these two equations, two unknowns by hand or by calculator or by MATLAB, I get 2.003 and 0.997. And you can very well see that 2.003 is very close to 2, 0.997 is very close to 1. So a small change in the coefficient matrix did not result in a large change in my solution vector. A small change in the coefficient matrix resulted in a small change in my solution vector. Let's, for sake of completion of the experiment, let's go and change the right hand side vector a little bit. So we have 1, 2, 2, 3 xy equal to, we'll change the right hand side a little bit. So let's suppose we make this to be 4.001 and this to be 7.001. So we are changing it by 1/1000th there, the right hand side vector. And when I solve this set of equations, I find out that, hey, my x and y turn out to be equal to 1.999 and 1.001. So again, this number is very close to 2 and this number is very close to 1. So a small change in the right hand side resulted in a small change in my solution vector. It did not result in a large change. So in this case, if I'm conducting this experiment, I'm finding out this particular system of equations is well conditioned. Again, we're going to figure out what we mean by a well-conditioned and ill-conditioned system of equations quantitatively, not by just conducting these simple experiments right here. This is just for illustration purposes, and we'll do that in the later segments. But this is a good example of getting started on at least understanding the concept of ill-conditioned and well-conditioned system of equations. And that is the end of this segment.